NMF stands for non-negative matrix factorization, and it's a type of algorithm that actually can be performed on any matrix, by which I mean a two-dimensional spreadsheet of data, right? And so this is an algorithm that is used for all sorts of things. It's actually one of the main algorithms that's used for like recommendation systems. So like when Netflix recommends to you, like you should watch this show, it's actually non-negative matrix factorization is either the algorithm that they're using or is one of the algorithms that they could be using. Is an algorithm that's often used for the sort of recommendation stuff. We're not using it that way here. The matrix that we're performing this operation on here is actually the two-dimensional spreadsheet of the FFT magnitudes in a buffer. So we have, time along the x-axis and the FFT magnitudes bins along the y-axis. We're going to start with our favorite drum loop here. Perform NMF here. I'm going to use fluid.buffNMF tilde. This is one of the objects in FluCoMa that only has a buff version. There is no fluid.nmf. We'll talk about these elements, these attributes in a moment, but first I'll just highlight for you that the salient information that I'm giving this object is the source, the drum loop buffer, and then this attribute at components 2. And what I'm saying is fluid buff NMF. Here is a buffer of sound. I think there are 2 things in here. Find for me 2 things. That's kind of all that I'm saying. And then it's going to use machine learning to try to deduce what are those 2 things. We'll just hear what it does first. So I'll bang this object. It'll bang me when it's done. And then we can listen to these two results. So I'm using Groove here to play back the this 2-channel buffer that it has given me. So there, it has taken this mono sound file of the drum loop and is playing back for me just the snare hits out of that drum loop. Here's the second one. So the second component it has found is just the kick and the hi-hat components. And it's been able to separate those 2 out. And when it does this, it actually writes those 2 new components into a 2-channel buffer. Right? The original drum loop is mono, but it writes these 2 components it finds and decomposes, separates out into the 2 channels of this 2-channel buffer. So now let's change it to 3. I'm going to give it the same source, the same drum loop. I'll say at components 3, and we'll see what it does. Bang it there, and then we'll listen to it. Here I'm just doing Groove again, playing a 3-channel buffer, and then a selector here so we can hear them in turn. So that sounds like it's just the resonance of the snare, right? It's just like the ringing tone of the snare head. Let's listen to the others. The second component is just the smack of the snare, just like that initial noisiness to it. And then the third component is, again, the kick and the hi-hat together as one component. I'm going to run it again. I'm just going to do the same process. I'm just going to ask the NMF algorithm to do the thing again. Let's see what we get now. So that's the whole snare, not the smack and the resonance separated out. Now we get just the hi-hat there, and so we can guess what the third one will be. And we get just the kick there. So this object, fluid buff NMF, has been able to analyze this buffer and separate out those 3 drum instruments from the mono buffer file. And we didn't tell it anything. We didn't tell it what a drum hit is. We didn't tell it that it was drums. We didn't tell it that it is going to be a sharp attack. We didn't tell it that there's going to be a low frequency part, a high frequency part, and then like a middle thing. We told it none of that. We just said the number 3. And this is what it's able to give us. So the way that it's doing this, So if we look at, this is a spectrogram of our drum loop here. We got the kick drums down here. We got the cymbal energy up here. And then we have the snare hits in here. And we can see this is the resonant parts of the snare, right? So that's where that snare ring is. If we just try to think about this loop, we have these different instruments that are sort of separated out here by color, just roughly speaking, right? We can see that there's a lot of overlap, not only in time, but also a lot of overlap in spectrum. And so we couldn't really use a slicer on this. If we tried to use a slicer, there are some times where the kick and the cymbal happen at the same time. And so even if we used a slicer, we would definitely still have slices where both of those instruments are present. Also, if we tried to use something like filtering or something, right, because the cymbals are high, the kicks are low, there's still a lot of overlap in the spectrum. So even trying to filter out the different drum instruments, that's not going to work either. So what the NMF object is actually doing is it's doing something more intelligent. It's not just looking vertically, it's not just looking horizontally, which is kind of like what HPSS was doing, right, comparing the vertical and the horizontal informations. It's actually looking at the spectrum and looking at each subsequent FFT frame through the whole buffer. And it's trying to identify where in the spectrum does energy tend to occur together. So these resonant pieces of the snare, they tend to always occur together, right? When this energy is present, these ones are also usually present. And this is the sort of relationships that it's looking for. What it's trying to do with that information is create spectral templates. In this case, however many you ask for. So first we asked for 2, then we asked for 3. It's going to try to find 3 spectral templates that it can use to summarize or explain a lot of the types of, a lot of the different FFT frames that it has here. So it looks at all the FFT frames and says, can I try to find 3 spectral templates that will be really useful in explaining all of the varieties of FFT frames that I have here? And so it says, okay, well, if this energy always tends to occur together, I should put all of that together in one template, because then that will explain a lot of the types of things that happen in these FFT frames. This energy, the energy in this bin and this bin and this bin and this bin and this bin, et cetera, that always tends to happen together, right? It happens together here, here, here. So I should put those together in a spectral template, and that will help me explain a lot of the things that happen in these FFT frames. And then the same for these high frequencies here, right? All of these partials of the symbol tend to happen together. So it puts all of that in one spectral template. It is really looking at the energy in the specific FFT bins. So if you had this snare hit, and it's the resonance is at a particular frequency, has these partials because of that fundamental frequency. If you were to shift the pitch of the snare, the algorithm here would have to consider that as a completely separate sound object. It would not be able to identify that as a snare because those energy partials would now be in different places. And so it really is dependent on really a pretty precise spectral template that it's looking to create. So once it does this process of making these spectral templates, it can return those to us, and we call those bases. This is a synonym for template, essentially. This is when we use the object, we call them the bases. Each individual one is called a basis, B-A-S-I-S, not a base. So it finds these 3 bases, and here we see these 3 bases that we were just hearing. Here's the kick. Here's the cymbal with all that high frequency energy. This is a spectrogram. These are frequency and loudness. And then here's the snare drum, where we can see the resonant partials of that snare head, right? And so it finds these spectral templates. And then we can actually have access to these and do some things with them. But when it creates these bases, at the exact same time it's creating bases, and it's also creating what are called activations. And the activations are, through time, from the beginning of this buffer to the end of the buffer, how present is each one of these bases at each FFT frame through the buffer. So here we see, we have the kick basis, frequency and loudness. Here's the low frequency energy of the kick. And this basis is this amount of present or active, because these are called activations, is this amount of activated at these moments in the drum loop. So we can see there's where the drum kicks happen. Same for the snare, same for the cymbal. And so it's a combination of these activations and bases that NMF does. When NMF does its decomposition process, when I hit the bang, it is looking at the buffer and trying to decompose it into activations and bases that, when recombined, could recreate the original sound. The way that we get our individual components, so then we can listen to just the kick, just the snare, just the hi-hat, is that it takes just the kick basis, combines it with just the kick activation, and then uses this spectral template, activates that spectral template at these moments in the buffer, and therefore resynthesizes just that part, just that kick drum. And it does the same with just the snare activation and bass, just the cymbal activation and bass, and then we get those three resynthesized components. So that's pretty cool. The resynthesis is like the sort of first most salient aspect of what buff NMF can do for us. Because, you know, this is like a pretty hip, pretty powerful thing to play around with sound with, separate out these different components. The way we're actually playing back those resynthesized components is I'm saying at components 3, then I'm also specifying an attribute resynth, which is going to be a buffer that it will write those resynthesized components into. And so because I'm saying at components 3, this buffer will end up being 3 channels with those 3 different components. Also, you need to specify resynth mode 1. That means 1 meaning true, and true meaning yes, please do the resynthesis for me. The default is 0 because we don't always want to do the resynthesis for reasons we'll see in a moment. And the resynthesis is actually a bit computationally expensive. And so we want to have a flag there where we can turn on and off whether or not that computationally expensive part should happen or not. So if you want to do the resynthesis part, you do have to turn that flag on. The things for which NMF will be most successful are when the templates that you're hoping that you will discover occur offset in time from each other and occur multiple times throughout the buffer. So this is a great example, which is why I use it for the demonstration, because we get the same spectral energy occurring multiple times through the buffer and offset from time. So NMF is really able to say, like, here's the thing that happens a bunch, and you know it happens separately from these other components. Okay, so we've done this. There's a whole other section. So once we actually have these activations and bases, we can also use them individually. So I'm giving fluid buff NMF here. I'm saying at activations, here's a buffer where you should write in the activations once you find them. Put those in a buffer, and those will look like this. Right, there they are. That's what we were looking to see. Our activations are contained in this buffer as 3 channels. And it does the same thing with the bases. I say at bases, here's a buffer with those bases. Snare, cymbal, and kick. If I tell play tilde to play these activations buffer, I will get these contours, you know, played through time. And I could use them to control the loudness of some signal. So here, I'm going to play the activations, and then I'm going to use them to control the loudness of this pink noise. So I can use them as amplitude curves that actually are performable with something like this. Also, I'll note for you that because these loudness curves are decomposed from the FFT analysis of the buffer, this isn't really information happening at the audio rate. It's happening at a much slower rate. In fact, it's happening at the hop size rate, because we'll have a new activation each FFT frame. So every hop size will get a new activation value. And the FluCoMa objects actually change the sample rate of these buffers so that when you play them back, they actually play back at the appropriate speed in something like play tilde, so that we can still have it at the rate that we would expect to hear that loudness curve change over time. Okay, here's a new object called fluid NMF filter. What this object does is we give it our buffer of bases, and it will use those as spectral filters to filter sound coming into it. So here I'm going to send in pink noise. That pink noise is going to be filtered by these spectral templates and then output of these outlets here. So I'm also going to use the activations to control the amplitude of those signals. I'm going to filter the pink noise so it sounds like the spectrum of the different drum instruments, and then I'm also going to apply the amplitude curves, the activations of the different drum instruments to sound like the hits, the rhythm of the drum instruments, and we'll get something like this. So these activations and bases we can use separately, and we can really start to think about ways of using them as spectral templates and loudness curves for different purposes. If I use NMF filter, rather than just sending noise through it, I could also send an audio signal through it. Here is the original drum loop playing in real time through NMF filter. So I'm not playing back a buffer here. I am playing back this buffer. But then I'm sending that real-time audio signal through NMF filter with the bases that were determined from the drum loop. So by sending in the original drum loop and using the snare basis, the snare spectral template as a filter, I get out just the snare in real time. And so this could be the sort of thing where, you know, if you have a live performance, you have a drummer on stage, you set up some mics, you record a little bit of them playing. You know, actually, you could just set up one mic, I guess, is the case here, because you have a mono audio signal. Record a little bit of their playing, decompose that buffer, and then they could be playing in real time into NMF filter, and you could actually get out here different audio streams of the different drum surfaces that they have in front of them, even from a mono input signal, all in real time using NMF filter. Also, if we play a different audio file into it, so not the original, but something like this. Here's just a sound file example. This is the original sound. And then we listen to that going through NMF filter. This is the snare basis. This is the hi-hat basis. And that's the kick basis. So you can hear that there's a lot of like bleed there, but it still actually somewhat captures these different parts of the drum kit in the original song. The reason there's all that bleed there is because NMF filter, the way that this object works is it needs to pass through all of the energy in the spectrum. It can't just like leave some out. And so it will find where is the best place for this piece of energy in the spectrum to be passed through, and it'll put it through one of those three filters. But it still can be, you know, provide some interesting results, again, happening in real time. Here's a new object, fluid NMF match. Now for NMF filter, we give it the bases and it does spectral filtering. For NMF match, we're going to give it the bases and it does spectral comparison and tries to match the signal to the spectral template. So when I play the drum loop through, for every FFT frame in this signal coming in, it's going to try to figure out how much does this moment in time right now match the kick template? How much does it match the snare template or basis? How much does it match the cymbal basis? And so what we get is a sort of real-time activation curve of when those different drum instruments are being hit. And we see the value spilling out here. And then this is a multi-slider. This is also a multi-slider, just in a different view setting. So we can sort of see how they happen over time. And you can see this is essentially the activation curve that we were getting in the buffer before, but now through a real-time signal. So again, this could be a live performer playing in real time, being sent through NMF match, and you could have triggers knowing when different drum instruments are being hit, almost like you had, drum triggers on the surfaces of drums triggering things, but all through a mono microphone signal. There's one catch or downside to this process of fluid buff NMF. So as you grow your buffer size that you want to analyze, the amount of time it takes to compute that grows exponentially. And so if you start to pass in big buffers that are many minutes or even like an hour, you'll have to let it run overnight, and maybe then even it won't finish. So people often think about doing something like this with a field recording. Like, what if I were to take a field recording and look for a particular bird call, right? Because that'll have a particular spectral template shape to it. I mean, bird calls also happen through time, and we're looking at spectral templates that are quite momentary. But the snare hit also happens through time, and we're able to find that as an object. So we would be able to find something like that. And so here's an example of a way that one would try to do that. So if we have this 22-second sound file that's sort of like a field recording. So perhaps I want to extract the dog barks. That's the thing I'm interested in. I want to know where there are dog barks, if it's a long recording, or I want to actually extract those dog barks into a separate component and be able to do something with them. Rather than trying to run NMF on the whole recording, what I'm going to do is I'm going to find part of the recording that has that spectral template in it that I know will be there. And I know that there are some dog barks in the first 3 seconds. So I'm going to copy out just the first 3 seconds into a separate buffer. And then I'm going to run the decomposition process on just that short buffer and get the bases out. And I only said 2 components. So I'm sort of thinking like dog bark and everything else. Like, I'm hoping that's what NMF will be able to separate out. And so here are my bases. And now if we use NMF match and just play back the whole sound file now, all 22 seconds, through NMF match that uses the bases that were discovered from just the 3-second analysis, I can find the dog barks through the entire field recording based on just a shorter analysis of the looking for the basis of the sound I'm interested in. So that's another way to think about approaching this stuff and sort of kind of navigate around the intense computation that NMF can require. Here's a way to sort of get at what you're looking for without having to try to let NMF, compute overnight or whatever.